Hello everybody. In this video we're going to solve an example on mass transfer coefficient calculation in packed beds. So here we have a packed bed at 37 degrees Celsius and 1 atmosphere, and we have air flowing through the packed bed as we see here in this photo here. And this packed bed is a bed of granular solids saturated with pure water. So you can think of this as like sponges or something that is highly saturated with liquid water. The rate of water evaporation is calculated using mass balance on the entering and exiting air, and it's found to be 9.428 grams per second. So by calculating the mass flow rate of water out and in, from the difference you can easily tell what is the rate of evaporation. We know the average particle diameter, which is 7.3 of the granular solids, and we know the void fraction, which is 0.67. The average superficial velocity of air is 0.82. So we know all these information. There is one detail here that we need to know before we proceed with the reading the rest of the problem statement, which is regarding the driving force. So we have here air. Let's say this air is, we don't know what is the amount of or partial pressure of water in this air, but let's say this air is pure air, so there is no water here. So as this air goes inside the column or passes through the column, the water evaporates from the granular solids. So as you go up, the partial pressure of water in the air increases. So it starts here with 0 and then it keeps increasing until it reaches its maximum value before it gets out of the column. So the driving force would be the partial pressure of water at the surface of the granular solids minus the partial pressure of water in the air. This is variable, and this partial pressure here is variable. It's not constant. It increases as you go from down to up. So the driving force is not constant. We are operating at constant temperature and pressure, and we say that this solid is saturated with water, so we can deal with this as pure water. This is water that's evaporating, and as we will see here, the problem statement states that the process is gas phase controlled and there is very little solid phase resistance, so there is no resistance in the solid phase, so you can assume that this is just water when considering the driving force, I mean. So this is constant, but this is variable. So we don't have a constant driving force that we can use in our equation. So for simplicity, we can assume that the partial pressure of water in air throughout the whole column will be considered as, or we will take this as the average value. So this average value will represent the whole column, and this to make this constant and to make our calculations easy. So the partial pressure of water vapor in air can be taken as the average throughout the bed, which is 1241 Pascal. We assume that the air properties are not affected by the evaporated water, which means that the air properties would be the properties of pure air. The density, the viscosity, the diffusion coefficient, everything is taken as that for pure air. We said that the process is gas phase controlled and there is very little solid phase resistance. So these are all known information, or information that we have just mentioned before. We need to calculate the area of mass transfer in the bed, the area that this bed provides for us. Before we proceed, we have to have like an idea what steps shall we follow. We can tell for these kind of problems, or in this course, that the area is only or in most of the cases is only available in one equation, which is the relation between the flux and the rate. This is the only place where we can find the area part of our calculations or part of our equations. So we know the rate, and if I can calculate the flux, then I can calculate the area. This is simply what I would do. So I listed all the information that I have here. This is the rate, the average particle diameter, the void fraction, the superficial velocity, pressure, temperature, P2, which is the partial pressure in air. Psat is P1, this P1 here, or PW1, which is the partial pressure of water at the surface of water. in the air, at the layer which is adjacent to the water, at the interface. So this is going to be the saturation pressure, which we can calculate using Antoine equation or get it from any textbook or reference, and then you will find that this is at 37 degrees Celsius, it will be 6204.5 Pascal. We will need the properties of air, so that's why we got this this table from the appendix. We have the temperature at 300 and 320. Our temperature is 310. So using linear interpolation, you can get the actual values at, or the values of the density and the viscosity at 310 degrees Kelvin, which are here. And keep in mind that this is or these are the properties of air, not water, because this is the mass transfer coefficient in air, because we said that the resistance is only in the gas phase. We will need the diffusion coefficient, and that's why I put this table. I'll come to it later, but the equation that we will use is that the air is the molar rate of evaporation divided by the molar flux, or the evaporation flux. The molar rate of evaporation is already given here, or the rate of evaporation is already given here, and we know the flux is kg multiplied by delta P. I know the rate and I know delta P, because this is the difference between these two values, so I need to get kg. But one thing I have to do is to make sure that the units are homogeneous for these two terms. So this is this term will produce the units of moles per meter square second. But this is what I have here is in grams per second, so I have to convert this from mass rate into molar rate. So the molar rate is mass divided by the molecular weight of water, of course. So now I have the numerator done. For the denominator, I need to get kg. So to get kg, I have to calculate Reynolds number, Schmidt number, and all these things, and then substitute in the relation that we have. But first, we need to make sure that the properties we have are ready to use. So the property that I have here is the density viscosity, and I need the diffusion coefficient. The diffusion coefficient of water in air is available at 298 degrees Kelvin, but our system is at 310. So I will multiply by T over T power 1.5. This is a relation that we know from chapter 22, from the very first chapter in this course. So we can calculate Schmidt number, Reynolds number, and again, keep in mind that the units are very, very important. You have to make sure that the units are homogeneous, that everything is put in the proper units. So this is something that you have to keep in mind. So I can calculate Schmidt number, Reynolds number, and then using this relation, which is the relation for calculating the mass transfer coefficient for packed bed, or for gases or vapor phase in packed bed. And then you can calculate JD. From JD you can calculate KC. And again, this was also a relation that we discussed in the previous video. So this is KC. You can calculate it from JD, which I just calculated, average velocity, which I know from here, Schmidt number, which I just calculated here. So I can calculate KC. KC is the mass transfer coefficient in the gas phase, but this is in the units of meters per second, so it's multiplied by difference in concentration. I need to get kg instead of kc. And we discussed in chapter 27 the relations between the mass transfer coefficients in the same phase, and this is something that we can do without even going back to the previous chapter, that you know that kg multiplied by delta P equals kc multiplied by delta C. And I know if this is an ideal gas, that C is P over RT, so kg equals kc over RT. This is something that you can easily derive. It's not a hard thing to do. So again, the units are important. I use R as 8.314. This is 314, it's not 134. I'll fix this. So it's 8.314 Pascal meter cubes per gram mole Kelvin. So this is meters per second. So the product would be gram moles per Pascal meter square second. Or if you want to use the units of kilomole in atmosphere, it's going to be like this. So now the last thing to do is to substitute here. and again, you have to make sure that you use the proper units. So I have this is in gram moles per second, so I would prefer to use this because this is in gram moles, this is gram moles, and I already have the pressures in Pascal, so this is going to be easy for me as well. I'll just pick the right values. So this is the rate, this is the mass transfer coefficient, this is the driving force. One thing that you can do is to check the units, make sure that they will cancel out. So this is gram moles per second, this is gram moles per meter square second Pascal, this is in Pascal, so the only unit left is meter square. So this is the area that we will end up with. If you want to use this value, then you have to use the atmosphere and to use this in kilogram moles. So both will give the same result. Anyways, so this is the area, and this is how we can calculate the mass transfer coefficient for such cases. By ending this problem, we end this chapter, and this is the last thing that we will cover here, and this is the end of the course. So I hope this course was useful, and I hope you learned a lot from it, and I'll see you later. Goodbye.